Good morning, dear students. In our previous classes, we are seeing about general principles and processes of isolation of elements, which is dealing with the metallurgy. In this chapter, in our previous classes, we had seen about what is metallurgy, what is ore, mineral ore, differences between mineral and ores, different types of ores. In the extraction of metals, what are the steps involved in it? That is concentration, extraction, refining. In concentration, we had seen about few methods like hydraulic washing, magnetic separation, froth flotation process, leaching, and then we had gone for extraction of metals. The extraction, the ores are being converted into metal oxides, and from there we are now learning about how to select a suitable reducing agent for a metal oxide to produce metal. For that purpose, we are learning the selection of reducing agent by using Illingham diagrams. So in today's class, let us see about Illingham diagrams. So Illingham is a scientist who explained us about the selection of suitable reducing agent for a metal oxide. For that, he had plotted graphs between delta G, that is Gibbs free energy, and temperature. As we had seen in our earlier classes, saying that in a natural process, when metal is converted into metal oxide by reacting with oxygen, it is an exothermic process. The entropy is getting decreased. Basing upon that one, we are seeing about how metal oxides are stable. And in this graph, we'll be seeing how the metal oxides are converted into metals, how we can select a reducing agent, whether the metal oxides are stable or not, thermally stable or not. All those things will be learning in this particular topic called as Illingham diagrams. So Illingham diagrams, it is the graphical representation of Gibbs energy or Gibbs free energy, which is first used by Illingham. This provides a sound basis for considering the choice of reducing agent in reduction of oxides. So how we can select a particular reducing agent for a particular metal oxide to produce the metal. These diagrams are called as Illingham diagrams. It is a graphical representation. So these diagrams are also predicting the feasibility of thermal reduction of an ore. Feasibility of thermal reduction. Thermal reduction means by heating, whether the metal oxide can be converted into metals. So these diagrams are also predicting the feasibility of thermal reduction of an ore. At the same time, these diagrams are also predicting the feasibility of selection of suitable reducing agent for a particular metal oxide. If you see the graph here, so in our previous class we had seen about this thing, that is the downward slope of formation of carbon monoxide from carbon. We had seen all the reasons behind that one, why it is a downward slope. Now, here you can see that this is the graphical representation of formation of magnesium oxide. Naturally, when magnesium is combining with oxygen to produce magnesium oxide, it is having its delta G value around minus 1100. So since its delta G value is minus 1100, this reaction is a spontaneous process and magnesium oxide is going to be stable. And here there is a sharp curve in the graph which we are going to explain particularly about these things in our next topics. Now on the screen you can see the formation of aluminum oxide Al2O3. So here when aluminum is reacting with oxygen naturally, it produces aluminum oxide. Aluminum oxide is otherwise called as alumina also. So it is also a straight chain. You can see the delta G value is around nearly 1150 minus 1150 kilojoules per mole. And as the temperature is increasing, you can see that the delta G value is also increasing. That means to say that as the temperature increases, the stability of the metal oxide decreases, because lesser the delta G value, more is the stability. In the next graph, you can see that formation of chromium oxide. Here also, chromium combines with oxygen naturally to produce chromium oxide, Cr2O3. Here also you can see that the graph shows upward slope. That means to say that as the temperature increases, delta G value also increases, due to which the stability decreases. So lesser the delta G value, more is the stability. So the next line shows the formation of zinc oxide. So naturally when zinc is combining with oxygen, it is producing zinc oxide. Here also you can see a sharp curve. We'll be explaining in the next slides why this sharp curve is coming. So here also you can see that as the temperature increases, there is an increase in the delta G value. That means to say that the stability of zinc oxide also decreases as the temperature is increased. So this is formation of carbon dioxide from carbon monoxide. So when we are dealing with metals, we are learning about carbon forming carbon monoxide, carbon forming carbon dioxide, and carbon monoxide forming carbon dioxide also we are learning. Why? Because in metallurgy, the selection of reducing agent is most important. It is being explained by Illingham diagrams. Here, carbon is mainly, or we can say that carbon is the most important reducing agent which we are using in order to extract the metals from metal oxides. So that is why we are learning carbon monoxide formed from carbon, carbon dioxide formed from carbon, and carbon dioxide formed from carbon monoxide also, because they are helping us in reducing the metal oxides to metals. So here also you can see carbon dioxide formed from carbon. This line is a parallel to temperature. In our previous class we had seen, this is because since there is no change in the entropy, that is entropy is becoming zero, due to which delta G is equal to minus delta H. So that is why there it is independent of temperature and it is always a parallel line to temperature. And next we are showing the formation of ferrous oxide, FeO. So as the temperature increases, here also we can see that the delta G value is increasing. That is to say that ferrous oxide stability also decreases. And this graph shows about the formation of cuprous oxide. When copper is naturally reacting with oxygen, it is producing copper oxide or cuprous oxide. It is also a graph showing upward slope, where as the temperature increases, delta G value also increases, to say that stability is decreasing. This is the formation of mercuric oxide, HgO, and this is the formation of silver oxide, Ag2O. You can see here, except the line of carbon monoxide formed from carbon, all the other lines are showing upward direction. And this line, that is carbon dioxide formed from carbon, this is a straight line which is parallel to temperature. Except these two lines, all the other lines are steeping upwards, to say that as the temperature increases, delta G value also increases. But as the delta G value is increasing, the stability of all these metal oxides are decreasing. This is the thing what we are learning from the graph, so called as Illingham diagrams. Illingham diagram is mainly for identifying or selecting the suitable reducing agent for a particular metal oxide. Now let us go for the other aspects of Illingham diagrams. So this is Illingham diagram. We are seeing about the features of Illingham diagrams. The first feature, the graph for the formation of metal oxides is a straight line with upward slope. So here, starting from magnesium, formation of magnesium oxide, formation of aluminum oxide, formation of chromium oxide, zinc oxide, iron oxide, copper oxide, mercuric oxide, silver oxide. All these lines are showing upward slope, which is saying us that they are increasing as the temperature increases. Delta G value is increasing as the temperature increases. And automatically stability is getting decreased on increase of temperature. The oxide stability is decreasing on increase of temperature. Here, at the cases of magnesium oxide, zinc oxide, and mercuric oxide, you can see I had highlighted those points where there is a sharp curve. There is a sudden change in the slope. Generally, these metal oxides, after the formation of metal oxides, as the temperature increases, at those particular temperatures, that is here at this particular temperature, and at this particular temperature, there may be a change in the phase. That is, we are calling it as a phase transition. Phase transition means solid converting into liquid phase, or liquid phase converting into vapor phase or gaseous phase. That is called as phase transition. Due to the phase transition of those metal oxides, you can see that there will be a sharp curve or a sudden change in the slope. So especially with respect to slope of magnesium oxide, zinc oxide, and mercuric oxide, you can identify this. These sharp curves are due to phase transition. You have to remember the word phase transition. Phase transition means conversion of solid phase to liquid phase to vapor phase. Now, in the cases of silver oxide and mercuric oxide, on the top you can see silver oxide and mercuric oxide are on the top. Here you can clearly see that they are crossing the line of zero. That is to say that as the temperature increases, their delta G value is becoming positive. The delta G values of mercuric oxide and silver oxide are becoming positive. That means to say that when the delta G value is negative, we are saying that that substance is stable. But as the delta G value increases and becomes a positive value, it is going to be unstable, highly unstable. So more the delta G value, less is the stability. So here, with respect to Illingham diagram for the formation of silver oxide and mercuric oxide, is at upper part of the diagram, that is Illingham diagram, and the decomposition temperatures are 600 and 700 Kelvin. That is, silver oxide will be decomposed at 600 Kelvin only, and mercuric oxide will be decomposed at 700 Kelvin respectively. This indicates that these oxides are unstable at moderate temperatures and will decompose on heating even in the absence of reducing agent. Without using a particular reducing agent, we can see that these metal oxides are converting into metals. So, in the three features of Illingham diagrams, the first one we are saying about the metal oxide, Illingham diagram of the metal oxide formation. So, always Illingham diagram for the metal oxide formation is an upward slope. That is to say that as the temperature increases, delta G value also increases. In the second feature, we are seeing about the sharp curve or sudden change in the slope for metal oxides like magnesium oxide, zinc oxide, and mercuric oxide. And this for this we had given a reason saying that phase transition. That is, due to the phase transition from solid phase to liquid phase or liquid phase to gaseous phase, this is happening. And such sharp curves or sudden change in the slope, such curves will be called as a kink, K-I-N-K. So in a graph, if there is a sharp curve or a sudden change in the graph, that is called as a kink, K-I-N-K. So we can see three kinks in this graph. And a third, we had seen about the thermal instability of silver oxide and mercuric oxide, because the delta G values on increase of temperature, they are becoming positive values for these two metal oxides, due to which we can see that they are thermally decomposable substances, because they are thermally unstable. On heating, they will be decomposed without use of any suitable reducing agent. Let us see the remaining features now. So the graph for the formation of carbon monoxide. So here you can see this is the graph for the formation of carbon monoxide. That is, when carbon is reacting with oxygen, carbon monoxide is formed. So here you can see that this graph is a straight line which is a downward slope, or we can say that negative slope is observed here. This is because the delta S value, because of the positive value of delta S. So you know that in the previous class we had seen how the delta S value is being calculated. Delta S, that is change in entropy, is equal to entropy of products minus entropy of reactants. If here in this equation you can see that 1 mole of a gas is converted into 2 moles of gas. In our previous class also we had seen 1 mole of a gas is converted into 2 moles of a gas. That is to say that entropy is increased. As entropy is increased, the delta S value becomes positive, due to which when we are substituting the positive value of delta S in the equation, delta G is equal to delta H minus T delta S. So automatically you can see that delta G will be always negative. Delta G is always negative. And here this is depending upon temperature. That is, as the temperature is increased, automatically you can see that delta G value is becoming more and more negative. When delta G value is more and more negative, automatically it is nothing but decreasing. So you can see that there is a decrease or there is a negative slope in the graph of carbon monoxide in the Illingham diagram. So the graph for the formation of carbon monoxide is a straight line with a negative slope. In this case, delta S is positive as 2 moles of carbon monoxide is formed by the consumption of 1 mole of a gas. It indicates that a carbon monoxide is more stable at higher temperature. That means as the temperature is increased, you can see that carbon monoxide is becoming more and more stable. So this particular graph is showing this. So you can see the line which is being highlighted here, which shows that downward slope of formation of carbon monoxide. And you can see that as the temperature is increasing, the delta G value is getting decreased. That means to say that carbon monoxide is becoming more and more stable. Next, the graph for the formation of carbon dioxide from carbon is a straight line parallel to temperature. So it is being highlighted here. So why is this? Because in our previous class, again, we had seen this one. That is 1 mole of a gas, that is 1 mole of oxygen is converted into 1 mole of carbon dioxide. So change in entropy delta S is equal to 1 minus 1, which is equal to 0. Since delta S is becoming 0, and when we are substituting the value in a delta G is equal to delta H minus T delta S, here delta H is a negative because it is an exothermic process, and delta S is 0. So automatically what happens is a delta G is equal to minus a delta H. And it is not having any term of temperature, due to which we can see that as the temperature increases, there is no effect on the delta G value. That is to say that this particular equation or particular reaction is independent of temperature. This is not depending upon temperature. That is why it is going to be a straight line parallel to temperature. Then the graph for the formation of carbon dioxide from carbon monoxide. You can see there is a graph showing the formation of carbon dioxide from carbon monoxide. So here, the carbon dioxide formed from carbon monoxide is a straight line with upward slope. Why? You can see here, 2 moles of carbon monoxide, which is a gas, 1 mole of oxygen, which is a gas, producing 2 moles of carbon dioxide. That means to say that in a reactant side, we are having 3 moles, and in product side, we are having 2 moles. So entropy delta S equal to 2 minus 3. That is, entropy of products is 2. Entropy of products is, reactants is 3. 2 minus 3 is equal to minus 1. That means to say that delta S value is negative. So delta S value at lower temperatures it is negative. As it is increasing, as the temperature is increasing, automatically you can see that the delta G value goes on increasing, same as metal oxides. So that is why this is showing an upward slope. You can clearly see an upward slope of formation of carbon dioxide from carbon monoxide. So in this features of Illingham diagrams, we had seen about formation of carbon monoxide from carbon, formation of carbon dioxide from carbon, and formation of carbon dioxide from carbon monoxide. Now let us see the significance of Illingham diagrams. Significance of Illingham diagrams. The positive slopes of metal oxide shows that stability decreases with increase in temperature. So from the first point we are saying the same thing. So as the temperature is increasing, delta G value is also increasing. As the delta G value increases, stability decreases. So this happens to all metal oxides. There is a sudden change in the slope for the metal oxides like magnesium oxide, zinc oxide, and mercuric oxide. So in our previous this thing also we had seen here. Here also I am showing you the sharp curves or sudden changes, which I am calling them as the graphs. If there is a sudden change, we are calling it as a kink, K-I-N-K, kink. So the kinks of magnesium oxide, zinc oxide, and mercuric oxide you can see here, which shows that there is a phase change from solid to liquid or liquid to vapor, solid phase to liquid phase, or liquid phase to vapor phase. And the negative slope of formation of carbon monoxide from carbon shows that carbon monoxide becomes more stable with increase in temperature. So carbon monoxide is becoming more and more stable with increase in temperature. With increase in temperature. So this also in our previous listing we had seen. But here there is a very important point, that is fourth point, tendency of the metal to undergo oxidation. So here we can see on the screen, there are metals like magnesium, aluminum, chromium, zinc, iron, copper, mercury and silver. Here you can see that the graph of magnesium oxide, the formation of magnesium oxide is showing at around minus 1100. And aluminum oxide showing at around minus 1050. Formation of chromium oxide is showing at nearly 700, minus 700 kilojoules per mole. Zinc oxide around minus 600 kilojoules per mole. Iron oxide around minus 500 kilojoules per mole. Around minus 300 you can see about copper. Around minus 100 you can see about mercuric oxide, and nearly to zero you can see silver oxide also. So here minus 1100, minus 1050, minus 500, all those things you can see that the delta G value is increasing. Delta G value is increasing. You can see here this is the delta G value increasing. As the delta G value increases, stability decreases. And the spontaneity of that reaction also decreases. Lesser the delta G value, more is the spontaneity of the process. That is to say that if the delta G value is very less, that reaction will be very spontaneous. That is why formation of magnesium oxide is having more tendency, because its delta G value is very less when compared to other metal oxides. So that is why tendency of formation of oxide for magnesium is very easy, very high than that of aluminum, than that of chromium, zinc, iron, copper, mercury and silver. That is to say that the tendency of the stability of the formation of oxides, or we can say that tendency of the metals to undergo oxidation decreases from magnesium to aluminum, aluminum to chromium, chromium to zinc, iron, copper, mercury and silver. So this goes on decreasing. Why? Because the delta G here, less the delta G value, more is the stability. So when the delta G value is less for a process, then that process is going to be spontaneous and that product formed is going to be more stable. So that, and this you can see here how the delta G value is increasing. The delta G of value of magnesium oxide is very less. So that is why tendency of the metal to undergo oxidation for magnesium is more. So this is the order which shows that the delta G value is increasing from magnesium oxide to aluminum oxide, chromium oxide, zinc oxide, ferrous oxide, cuprous oxide, mercuric oxide and silver oxide. So as the delta G value is going on increasing there, automatically stability is decreasing. So that is why magnesium is having more tendency to undergo oxidation. You can see the order clearly. Now let us see the importance of Illingham diagrams. So importance of Illingham diagrams, how we are going to use Illingham diagram in each case. That is the thing we are going to learn here. So these things, that is each point what I am going to discuss now, will be a very important 2 marks question in your PUC. You can see here, the first one I had taken as Illingham diagram for the formation of magnesium oxide and aluminum oxide. So when we are seeing about the Elingham diagrams of magnesium oxide and aluminum oxide, what we are going to learn from it, that is the thing we are going to see here. So that is why I had taken only magnesium graph of magnesium oxide and aluminum oxide here. Here, the first point I had to say you, the graph with respect to magnesium oxide, we are having a sharp curve here because the melting point of magnesium oxide is at this particular temperature. At this particular temperature, there is the melting point of magnesium oxide, due to which there is a change in phase, that is a solid phase to liquid phase, due to which you can see that there is a sharp curve or a sudden change in this graph due to the melting point of magnesium oxide. Now, here from the graph you can see that the delta G value of formation of magnesium oxide is less than that of delta G value of formation of aluminum oxide, because here you can see that the delta G value of magnesium oxide is nearly somewhere around minus 1100 kilojoules per mole, whereas this is near to 1000. So that is why we can see that since delta G value here, the delta G value of magnesium oxide is less than that of delta G value of aluminum oxide. From that, what we are going to say, that is magnesium oxide is more stable than that of aluminum oxide at less than 1350 degrees centigrade. Why? Because here you can see that here there is an intersection. Up to this intersection, you can see that line of magnesium oxide is below and line of aluminum oxide is on the top, due to which up to this particular temperature, magnesium oxide is more stable because the delta G value will be less, whereas above 1350 degrees centigrade, the magnesium oxide is going up and the line of aluminum oxide is coming down due to this intersection here, due to which here you can see that above 1350 degrees centigrade, aluminum oxide is more stable than that of magnesium oxide. Aluminum oxide is more stable than that of magnesium oxide. So below 1350 degrees centigrade, you can see that magnesium can be used as a reducing agent for alumina. That is, when alumina is reacting with a magnesium metal, aluminum metal is formed and magnesium oxide is released. Here, magnesium oxide is more stable, that is why it is in the product side. Alumina is in reactant side because this is less stable. This happens only at below 1350 degrees centigrade. But this particular process is not used. Why? Because this particular process, that is using of magnesium for reduction of aluminum oxide, practically it is possible, but economically it is not useful. So that is why this particular equation or reaction is not used commercially for the preparation of aluminum. A simple reason, because magnesium is costlier than that of aluminum. Since magnesium is costlier than that of aluminum, this particular process is not economical. But above 1350 degrees centigrade, when the temperature is more than 1350 degrees centigrade, you can see that the line of aluminum is coming down and the line of magnesium is going up. Magnesium oxide is going up and the line of aluminum oxide is coming down. That means to say that above 1350 degrees centigrade, magnesium oxide is less stable than that of aluminum oxide, or we can say that aluminum oxide is more stable than that of magnesium oxide above 1350 degrees centigrade, due to which we can use aluminum as a reducing agent for magnesium oxide to see that a magnesium metal is produced. So let us see the same topic once again because it is an important thing. So I am repeating it. So we are discussing about importance of Illingham diagrams. In this importance of Illingham diagrams, first thing we are going to see is about the Illingham diagram of magnesium oxide and aluminum oxide or alumina. From the graph, we are able to see that magnesium oxide is more stable than that of aluminum oxide because the delta G value of magnesium oxide is less and the delta G value of aluminum oxide is more. But this is only up to the temperature, a particular temperature called as 1350 degrees centigrade. But above 1350 degrees centigrade, it is getting reversed. That is to say that aluminum oxide is having less delta G value than that of magnesium oxide. That is why above 1350 degrees centigrade, alumina Al2O3 is more stable than that of magnesia, that is MgO, magnesium oxide. So here, initially what we are seeing, the delta G value of magnesium oxide is less than that of delta G value of aluminum oxide. This is happening up to 1350 degrees centigrade. So that is why magnesium oxide is more stable than that of aluminum oxide below 1350 degrees centigrade. So since magnesium oxide is more stable than that of aluminum oxide below 1350 degrees centigrade, we are using magnesium. We can use magnesium as the suitable reducing agent to reduce alumina, such that Al2O3 reacts with magnesium to produce aluminum. But above 1350 degrees centigrade, so but this particular process is not used because this is not economical. But above 1350 degrees centigrade, aluminum can be used as reducing agent for magnesium oxide. Why? Because alumina is Al2O3 is more stable than that of Al2O3 is more stable than that of MgO. So that is why we can see that magnesium oxide can be reduced by using aluminum metal to produce magnesium metal. This is an important 2 marks question. We have to see that we are drawing the graph and we are explaining all these points for the Illingham diagrams of magnesium oxide and alumina. Let us see the next importance. Illingham diagram for the formation of mercuric oxide and silver oxide. Illingham diagram for the formation of mercuric oxide and silver oxide. So for that I am highlighting only those two. You can see mercuric oxide and silver oxide. Here, as the temperature is increasing, the graph shows that initially they are having their delta G values as negative values only. That is around minus 100 and minus 50 kilojoules per mole. But as the temperature is increasing, automatically the delta G values are becoming positive. The delta G values are becoming positive. So as the delta G values are becoming positive, we can say that we can predict that as the temperature increases, the stability of mercuric oxide and silver oxide is decreased drastically. The stabilities of mercuric oxide and silver oxide is decreasing drastically. That is to say that they are thermally decomposable substances. To say that they are thermally decomposable substances. So in both the cases, line of delta G crosses the line of 0. That is to say that they are becoming positive values. And here one more point we have to remember, that is there is a sharp curve or a sudden change in the graph of mercuric oxide, because due to the melting point of mercuric oxide is at this particular temperature, due to which there is a change in phase, solid phase to liquid phase, due to which you can see that there is a sharp curve here, sharp curve, kink. So in both the cases, line of delta G value crosses the line of 0. That is, as the temperature increases, the delta G value becomes positive. So they are unstable on increasing the temperature. This is saying that they are unstable on increasing the temperature. So such substances are called as thermally unstable substances. Mercuric oxide HgO and silver oxide Ag2O are thermally unstable substances. So that is, they can be easily decomposed by heating. That is, on heating, we can see that they are easily decomposable. So that is why at 700 Kelvin, that is 427 degrees centigrade, mercuric oxide on heating produces mercury. And at 327 degrees centigrade, that is 600 Kelvin, silver oxide converts into silver on heating. So this particular equation, that is silver, this particular equation what you are seeing on the screen here, that is silver oxide. Here there is a small mistake, 2Ag2O. It is 2Ag2O gives rise to 4Ag plus O2. It is given as A2 here. It is not A2, it is Ag. Ag2O. Ag2O, silver oxide, gives rise to 4Ag plus O2. Please correct that. And also this equation is important. See, when people, so silver is the metal what we use at home in the form of jewelry and so on. Silver goes on converted into black, because when it is exposed to atmospheric air, easily it converts into silver oxide Ag2O. As it is converted into silver oxide, it is giving as a dark greenish texture over the silver. So when you take this one to the silver shop to clean it, they see that it is heated strongly. That means to say that they will be heating at the temperature more than 600 Kelvin or 327 degrees centigrade, due to which whatever oxide layer formed on the silver is converted into silver, producing oxygen gas. So this is the thing what they'll be doing in the jewelry shop to see that your silver is shining by heating. They'll be seeing that whatever oxide layer of silver formed over the jewelry, they'll be removing it by heating at 327 degrees centigrade or 600 Kelvin of temperature. So once again, we can see this importance of Illingham diagram. So in this second point of importance of Illingham diagram for the formation of mercuric oxide and silver oxide we are learning here. So here mercuric oxide, you can see there is a sharp curve in the graph. This is due to melting point of the mercuric oxide, due to which there is a sharp curve or a sudden change. This particular change is called as kink, due to the change in solid phase to liquid phase. And then these two graphs are crossing the line of zero, that is delta G values are becoming positive on increase of temperature. So as the temperature is increased, their delta G value are becoming positive, due to which they are said to be unstable on increase of temperature. That such substances are called as thermally unstable substances. That is, on heating, they can be converted into metals. So this equation, you can see that 2HgO gives rise to 2Hg plus O2 at 700 Kelvin of temperature. And at 600 Kelvin of temperature, you can see that Ag2O is converted into Ag. That is, 2Ag2O gives rise to 4Ag plus O2. Now let us see the next importance of Illingham diagram. That is Illingham diagram with respect to zinc oxide. So for that purpose, I am saying that the remaining lines are removed. Zinc oxide. So here zinc oxide is, you can see that here also there is a purpose of explanation for the kink. That is a sharp curve or sudden change in the slope just because of conversion of zinc oxide solid into vapors. So there is a change in phase from solid phase to vapor phase, due to which you can see that there is a sharp curve in the graph. Next to that, if you see, zinc oxide is stable up to 800 degrees centigrade. That is to say that this particular temperature, you can see this particular intersection, this is stable. Zinc oxide is stable up to 800 Kelvin, but above that is unstable. Why? Because here the line of carbon monoxide is coming down, whereas the line of zinc oxide is going up, due to which zinc oxide is stable than that of carbon monoxide below 800 degrees centigrade. So below 800 degrees centigrade, you can see that zinc oxide is more stable than that of carbon monoxide. But above 800 degrees centigrade, you can see that carbon monoxide is more stable than that of zinc oxide. Carbon monoxide is more stable than that of zinc oxide. So that is why we are going to use coke, that is carbon, as the suitable reducing agent to reduce zinc oxide to produce zinc metal. Zinc metal. So this is the Illingham diagram for the formation of zinc oxide. So from the graph, it is clearly evident that there is a sharp curve, that is due to the phase transition of the phase. That is to say that solid phase is converted into vapor phase, due to which we can see a sharp curve in the graph. Then from the graph, you can see that when we are comparing the stabilities of carbon monoxide and zinc oxide is stable below 800 degrees centigrade, and carbon monoxide is unstable at the same temperature. I mean, when compared to zinc oxide here. But above 800 degrees centigrade, carbon monoxide is becoming more stable than that of zinc oxide. That is why above 800 degrees centigrade, we are using carbon, that is coke, as the suitable reducing agent for zinc oxide. That is the equation given there. ZnO plus coke C gives rise to zinc plus carbon monoxide. Let us see the next importance. Illingham diagram for the formation of cuprous oxide. So here you can see that all these magnesium, aluminum, chromium, zinc, iron, all these are below copper. All these are below copper in the Illingham diagram. That means to say that cuprous oxide is above metal oxides like magnesium oxide, aluminum oxide, chromium oxide, zinc oxide, iron oxide, carbon monoxide, and carbon dioxide also. That means to say that all these lines which are below cuprous oxide are stable. All these oxides are stable, whereas cuprous oxide is unstable when compared to these things. So that is why when these metal oxides are stable, we can see that those metals can be used as reducing agents. Magnesium, aluminum, chromium, zinc, iron, carbon, and carbon monoxide can be used as reducing agents. You can see the equations. When cuprous oxide is reduced with magnesium metal, copper metal can be formed. In the same way, when cuprous oxide is reacting with aluminum, you can see that copper is produced here. In the same way, zinc, when cuprous oxide is reacting with zinc, you can see that copper is produced. When cuprous oxide is reacting with chromium, you can see that copper is produced. When cuprous oxide is reacting with iron, you can see that copper is produced here. And here this is the most useful because iron is cheaper than that of copper, and it is mostly used in many cases when we want to extract copper metal from the scrap. We'll be using this thing. A simple example I am showing you on the screen here. The blue colored solution, what is shown on the screen, is a copper sulfate solution. In that copper sulfate solution, if an iron nail is left for some time, you can see that the brownish layer formed over the nail is nothing but copper. Copper is deposited over the surface of iron because the Cu plus 2 ions gets reduced in the presence of iron to produce copper. The Cu plus 2 ions gets reduced in the presence of iron to produce copper. So that is why you can see that when a nail is left over in copper sulfate solution, it forms a layer of copper on the iron nail. On the iron nail, we can see that a layer of copper is produced, due to which copper is deposited on nail, iron nail. So cuprous oxide can also be reduced by using carbon monoxide to produce carbon dioxide and copper. But most economical way of forming copper is when cuprous oxide is reacting with coke. You can see that copper is produced.